Hello, this is Mr. Miller. Welcome to video 2D, more about finding limits. So in this video, for the most part, we're going to focus on rational functions, finding limits of rational functions. There is no problem finding limits as long as you stay away from the values that make the denominator zero. We want to start exploring what happens though when the denominator is zero. For instance, in this rational function, the denominator is 0 at x equals 3. That would make that factor 0. And the function has a hole there. Okay, a hole's not a problem. The limit exists as x approaches 3 where the hole is. That's not a problem. In fact, the value is about a half. The other thing that can happen when the denominator is 0 is that it has an asymptote there, which is totally different. As x approaches 1 in this graph, it approaches negative infinity on the left and positive infinity on the right. So we want to be able to tell when the function has a hole or not and how to evaluate the limit when it has a hole. Okay, here we go. So first, I want to review a little bit polynomial functions. We have a beautiful polynomial function here. Okay, 3x cubed minus 2x squared plus 4. And here's the graph of this function. It's very smooth. In fact, polynomial functions, when we find the limit as x approaches a value like 1, are very nice because the limit actually equals the value of the function there. So right here, this is x equals 1 where this green dashed line is. And we see as we follow the curve from the left, it equals 5. And as we follow it from the right, the limit is 5. This is 5 right here. So that point is 5. And that's the actual value of the function there. So for polynomial functions, evaluating the limit is easy. It's the actual value of the graph or the function at that point. So all we have to do is substitute 1 into here. If we didn't have the graph, that's what we would do. So it'd be 3 times 1 cubed minus 2 times 1 squared plus 4. I just substituted 1 into the polynomial. And this would be 3 minus 2 plus 4, which is 5. Same thing we see in the graph. So evaluating the limit of a polynomial function is easy. It kind of makes sense. As x approaches 1, this first term is approaching 3. The second term is approaching negative 2. And this term is approaching 4. 3 minus 2 plus 4 is 5. Okay. Here's a little bit more complicated function. Square root of x minus 1 over 4 over x minus 4. But we're finding the limit as x approaches 3. And 3 is not a value that makes the denominator 0. It's kind of like the safe zone for the function. The only thing we'd have to be concerned about is if we were finding the limit as x approaches 4, because that makes the denominator 0. But we're not. We're finding the limit as x approaches 3. That corresponds to this point in the graph. And again, the limit as we approach from the left and as we approach from the right equals the value of the function. So even when we have something like this, we can simply just substitute the number into the function. So it'd be the square root of 3 minus 1 over 3 minus 4, which is square root of 2, excuse me, over negative 1, which is minus square root of 2, which is about minus 1.41 something. So that's where this is right here. This is minus 1, minus 1.5. It's a little shy of minus 1.5. Okay, so this is minus square root of 2. So lovely. As long as we're not finding the limit where the denominator is 0, no problem. Okay, now here we have a rational function. Okay, so as x approaches 4, well, it turns out that 4 makes the numerator and the denominator 0 in this case. So 4 is one of the problem points. We want to find out if 4 is a whole or an asymptote. So what we're going to do is simplify this function. This is equal to the limit as x approaches 4, and we're going to factor the numerator and the denominator. We can use our TI-89 to do this. So the numerator factors into x minus 4 and x minus 1. And the denominator factors into x minus 4 and x plus 2. Okay, so we see the factor that goes with 4 cancels. That means it was a whole. So there's a whole at x equals 4. And so this is equal to the limit as x approaches 4 of x minus 1 over x plus 2. Okay, so since there's a whole and it doesn't affect the limit at all, it's just the limit of the expression that's left. Okay, so you might want to ask, what's the difference between this whole mess and this mess right here, this smaller mess? What's the difference? The only difference is this top one is not defined at 4 and this one is. But as we take the limit, we don't care what it is at 4. It's only what it approaches. And these two are the same in what they approach as x approaches 4. So all I got to do is put in 4 now. Because this is defined at 4. 4 isn't a problem. It doesn't make the denominator 0 in this one. So it'd be 4 minus 1 over 4 plus 2, which is 3/6, which is 1/2. So in this graph, it's a little bit hard to see because x approaches 4. 4 is right here. This is the point we're talking about. Now, the original function would have a hole there. It would look like kind of what I drew there with a hole. This one is the one that's actually graphed without a hole. They both approach a half at x equals 4. All right, so the bottom line is we got to determine if there's a hole or an asymptote there. And if there's a hole there, it's fine. We just cancel the term and find the limit. Okay, let's check out this one. So we don't have a graph this time, but we don't need one. We can do this without. That's kind of the whole point. We want to learn how to do these without even looking at the picture. So this is the limit as x approaches 3. If we use our calculator, the top factors into x minus 3 times x plus 3. The bottom is a little bit crazy. This is called the difference of cubes formula. And you can use your TI-89 to factor it. It factors into x minus 3 times x squared plus 6x plus 9. Okay, so we're finding the limit as x approaches 3. Alright, well, that corresponds to this factor and it cancels out. So there must be a hole at x equals 3. So that's fine. Whatever the graph looks like, there's kind of a hole there, and whether there's a hole there or not, the limit is the same. So this is going to equal the limit as x approaches 3 of x plus 3 over x squared plus 6x plus 9. Okay, so this graph would have a hole, this graph doesn't. They both have the same limit, so we can just evaluate this now. As we put in 3, in the numerator we get 3 plus 3, which is 6. In the denominator we get 3 squared, which is 9, plus 6 times 3 is 18, plus 9. I think that's 18 plus 18 is 36, so I get 6 over 36, which is 1/6. Alright, so our strategy with rational functions is to factor, kind of take note of whether it's an asymptote there or a hole. If it cancels, we just evaluate what's left. Okay, so the limit is 1/6. Alright, I have one more example here. So the limit as x approaches -2 of this function here. So our strategy is factor it and see what happens. So this is the limit as x approaches -2. In the numerator we have x minus 7. In the denominator we have x minus 7 times x plus 2. Okay, this time the value we're taking the limit at corresponds to this factor, which doesn't cancel. That still cancels, but we still have an x plus 2 here, and when we put a -2, it's 0. We have an asymptote at x equals -2. So both functions, both the original and the simplified one, which would be 1 over x plus 2, have an asymptote there. So the limit does not exist. Okay, so holes are not a problem. We just cancel the factors and evaluate the expression. Asymptotes are places where the graph's going to either plus or minus infinity. Okay, I have an exercise for you. So here, consider this function. It's a rational function. I want you to factor it and determine, is x equal 1 a location of an asymptote or a hole? The same thing for x equals -3. Okay, determine if that's an asymptote or a hole. Then find the limit as x approaches 1 and the limit as x approaches -3. Okay, good luck.